Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 5th episode in a series that seeks to demystify programming in assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so you know when the next episodes come out. And start this playlist from the beginning. So far in this series, we have introduced the basic concepts of assembly programming, learned how to access memory in different ways through addressing modes, how to implement flow control with branching and subroutines, and how the 65C02 handles basic arithmetic and logic. In each episode, we touched on how the program stack was used, but this lesson is going to be completely devoted to this very important part of memory. Like a stack of pancakes, you can't access any byte on the program stack except for the one on the top. Otherwise, your whole breakfast/program will be ruined. First, let's take another look at the X16 Memory Map. Like all 6502-based systems, the X16 stack is on page 1, that is from hex 100 to 1FF. That's only 256 bytes, so it's not a lot of stack space compared to modern computers, or even not so modern computers. Even a 16-bit computer is likely to support a much larger stack. But this is what we have to work with, so we need to use it wisely and carefully. Now let's take a closer look at how the stack actually works. As we saw before, the stack pointer register, also known as SP or simply S, is only an 8-bit register, so we can always assume the stack pointer is referencing page 1. If the stack is empty, the stack pointer should reference the RAM address hex 1FF, so the SP register will be simply FF. When you push a byte to the stack, that byte will be written to the top of the stack, which is what the stack pointer references. Then the stack pointer is decremented, referencing the new top. When you pull a byte from the stack, you are loading the value from the address after the stack pointer, then incrementing the stack pointer, bringing the top down a notch lower, back to the address that was just loaded from, and is now free to have something else pushed to it. To illustrate how this works, we're going to step through the little program you see here. We are placing the start of the snippet at hex 1000, which we will assume is being jumped to from some startup vector. Then we initialize X with hex FF and transfer that to the stack pointer, effectively resetting the stack, as you would when powering on any 6502 system. Then we push that value in X to the stack, bringing the stack pointer up a notch. Then we call a subroutine called foo. So that means we will be pushing a 16-bit return address to the stack and then jumping to foo. There, we transfer the new stack pointer value back to X, which should reflect the fact that the stack is now 3 bytes deep. Then we return from the subroutine, meaning that the return address will be pulled off the stack, and we jump to the next instruction after the JSR. At that point, we pull the original value, which should still be FF, back into X, and then a break as we have nothing left to do and an empty stack with nowhere to return to. So now let's step through and see how the registers and the stack change with each instruction. Before executing this code, we are only going to assume that the program counter, or PC, has been set to hex 1000 and that everything else could be filled with random garbage. For each step, we will see what the values of the PC, stack pointer, and X register are going in, and then what the values of those registers will be going out, as well as the resulting contents of the stack. So the load X will give us a known value for X of FF, and increment the PC by 2. Everything else is still uninitialized and could still have random garbage from power on. Then we transfer the value of FF from X to the stack pointer register, and the stack is now initialized as empty. But nothing has been written to page 1 yet, but at least all the registers we care about are finally initialized. Here we push that value to the stack, which will result in the stack pointer going down to FE, and the first write to memory with FF as the first value on the stack. Next we see the jump to the foo subroutine, so a bunch of stuff is going to happen. Rather than just going to the next instruction address, the PC is going to be set to the address of foo, which is hex 1009. Then the return address is pushed onto the stack. That means that 2 bytes are written, starting with the high byte of the address as the previous stack pointer location, then the low byte of the address on top of that. As you can see, the address is effectively hex 1006, but that seems a bit weird. As you can see in the code, there is no instruction that starts at that address, so the PC should never go there. That's because the 6502 actually pushes the address 1 byte before where the PC should go after the subroutine returns. I'm not going to go into why the folks that designed the 6502 made that decision, so for now let's just accept that and move on. So now we can see that the stack pointer is now going to FC to account for those 2 bytes, and we're ready to start executing the subroutine. In foo, we simply transfer the stack pointer to X so that both registers now contain FC. Then we return, so the processor is going to pull the return address off the stack, add 1 to it, and place that in the PC. And then the stack pointer is incremented by 2 to free up those bytes that were pulled, and we're going to continue the main part of the program. Right after the subroutine call, we pull the last byte off the stack into X, restoring it to its original value, along with the stack pointer, which was incremented, so now both are FF again. The PC moves on to the following break instruction, so we'll just stop right there. We'll see how break and some other sundry instructions work in a later episode. At this time, we're going to look a bit deeper into what we saw. Now, we've seen JSR a few times in this series so far, but now we're going to look at it formally. We just saw how the registers and stack react to it, so let's go over it bit by bit. JSR only supports the absolute addressing mode, so the address to jump to will be the operand, so that gets put into PC instead of the next instruction address in the code. The stack pointer is decremented by 2 to indicate that 2 bytes were added to the stack. Those 2 bytes will be the current PC address plus 2, with the high byte going into the current top of the stack. The low byte of that address is put above that, and then the new value of the stack pointer will point above that. We've seen RTS a bunch too, and it simply needs to unroll what JSR did. The next value of the PC needs to be pulled from the stack, with the low byte first followed by the high byte, then the whole 16-bit address needs to be incremented. With those 2 bytes off the stack pointer will then be incremented by 2. One instruction we haven't seen yet is RTI, or return from interrupt. We're going to cover interrupts in another episode, but just know for now that it does something quite a bit different from RTS. Because the interrupted instruction is yet to be executed, the current PC is first pushed to the stack when an interrupt occurs, followed by the status register. So after an RTI, the status register is first restored, then the PC, so that the program may continue as it was. As we will see in that later episode, the interrupt can change the other registers, so they may also need to be pushed to the stack during the interrupt service routine and restored before the RTI. There are 4 push instructions for the 65C02, all of which will store a register value at the stack pointer address, then decrement the stack pointer. All of them only use implied addressing, so they never take any operands. PHA will push the A value, and PHP will push the processor status, and both of those are original of the 6502. The 65C02 adds support for pushing both X and Y directly, rather than having to transfer them through the accumulator like in older processors. There are also 4 pull instructions for the 65C02, which will reverse the corresponding push functions. Again, the instructions for pulling from the stack directly into X and Y were introduced for the 65C02 and are not available for older processors. For each of them, the byte in the position below the top will be loaded into the register and the stack pointer will be incremented. This makes the new top where the byte was pushed before, and it will be overwritten by a future push. The 6502 has a pair of instructions, which we saw in the earlier example, for transferring values between the X and stack pointer registers. TSX will safely store the current stack pointer low byte into X, which could be used for various calculations. TXS will go the other way, transferring the value from X into the stack pointer register, which will reset the stack to a new size. This is generally only done shortly after power on to initialize the computer, as the registers will usually contain random garbage at first. But if you really know what you are doing, you can call it later to perform another reset, but calling it in the middle of a program is likely to cause real problems. Generally, you never need to do it with the X16, as it will destroy your ability to go back to the basic interpreter without a full reset. But if you really need to get that extra bit of stack and don't care about going back to basic, proceed with caution. Beyond resetting the stack pointer, it is really easy to screw everything up by mismanaging the stack. High-level languages use their syntax to prevent some bad behavior but that could also influence programmers to use a lax approach when moving to assembly. It is imperative that you push and pull data in the exact opposite order. You can't pull data back out of order or move stuff up and down the stack. If you push anything during a subroutine or interrupt service routine, also known as an ISR, it must be pulled back before returning, or the PC will be sent off into the wilderness with an invalid address. This is probably the most common cause of assembly programs crashing. That and the inverse issue of overpulling, which is taking too much data off the stack before expected. You could pull the return address completely off the stack before the return and jump up a level accidentally. This could be even harder to debug if the subroutine was called shortly before the end of another subroutine, and the effects don't become apparent until much later in the execution. And as we said in the beginning of this lesson, the 6502 stack is only 256 bytes in total. You can't throw a whole lot up there at once, even if you have megabytes of total RAM. Recursion can be a very dangerous proposition, opening up the possibility of a stack overflow. It's not just a helpful website, folks, but a real disaster for your program. Finally, as we said during the RTI discussion, it is very likely that an interrupt will require 6 or more bytes of headroom on the stack at any time, so conservation is really important. I think that's enough scare tactics for now. Let's get into the example program for this lesson. We're going to create a program that verifies some of this stack behavior by printing out register values as it goes. So we're going to need the carout function address again, and constants for the new line and space characters in Petsky. Then we will jump over some data, which in this case is just a string. We want the first thing printed out to be a header showing which register values are in which columns. We define this with the ASCII Z control code, which will place the following string into that location of memory, followed by a 0 or null character, indicating the end of the string. You'll see that we used lowercase letters, and that's just what CA65 requires. For Petsky, it transcodes from ASCII using what the expected keystrokes would be. That means with the default graphical character set, typing letters without shifting will input uppercase characters. If you were to hold shift, they would be graphical characters, which is what you would see if your source had capital letters in a string literal. It is very confusing, especially for non-Commodore folks, but that's how the X16 works. At the start of the program, we print out that header by initializing a loop using the X register to iterate through the header string. In each iteration, we read a character from the screen and branch to @header_done if we've reached the end. Otherwise, we use carout to print the character to the screen, increment X, and loop back again. Once we have fallen out of the loop, we print out a new line character, and we're ready to start printing out some register values in the order of this header. First, we print out the initial values using a new subroutine called printRegs. We'll see how that works soon. For now, assume that it will print out all the current values followed by a new line, and the register values should stay the same as they were before you called it. Then we load up new values for A, X, and Y and printRegs again. So we should expect to see these values on the second data line. Next we do a push A, so we should see the stack pointer decrement with the following printRegs as that A value is placed on the top of the stack. The TSX instruction will replace the value in X with the one in the stack pointer. So the value we just loaded into X earlier will go away, and the two registers should match in the following printRegs. Now we do a PHP to put the current status on the stack, causing the stack pointer to decrement again. After printing that out, we do a PLY, which will pull that status byte into Y, so now we should have two pairs of matching registers as the stack pointer increments back to its earlier address that had been transferred to X. When we clear out the stack data, we pushed with a PLP, which pulls the former A value into the status register. As our numbers of pushes and pulls finally match, it is safe to return back to BASIC. After the main body of the program, we can define the printReg subroutine. First, we want to make sure that the registers that will be modified during the subroutine can be restored before it returns. So we push the status, A, X, and then the status again for use in the subroutine, and we are good to start. A still has its original value, so we can call the print hex subroutine we wrote in the last lesson to print out its value in hex characters. That will blow away the value in A, but that's okay as we have it stored on the stack now. Now we want to print out a space, So we load A with the space character code, as we can just overwrite it as much as we want now. Then we call char out to print that space, and we're ready to move on to printing the value of x. To do this, we transfer the value in x, which is still the original one, into A and call print hex again, then print another space. Then we do the same thing with y, which doesn't get modified at all in print regs, so it doesn't even need to be saved on the stack. Now we get to the tricky part. We need to print out the stack pointer, but we have already pushed a bunch of stuff to the stack since print regs was called, including the return address, so we're going to need to calculate that. We can do that by transferring the current value to x, and then again to A, as we can't just do that in a single instruction. Then we add 6, as we have pushed 4 bytes and the 2-byte return address since the initial call. So that should get us back to the value we are looking for. We print that out in another space, and then we are ready to print out the status. Well, that has certainly changed with all the math and stuff, but luckily, the value we want is right on the top of the stack, almost like we planned it. Now we can pull it back into any register, so we just pull it back to A so we can print it out. We print out that last byte, and then instead of printing another space, we print out a new line. And we are done printing all the output. Now we can restore those 3 registers we pushed to the stack, in the reverse order, remember, and return safely, knowing that the registers and status are all back to where they were before the subroutine was called. So now let's see it in the text editor. Okay, we're back in Atom, my preferred text editor, but you can use whatever you want. We see that now familiar boilerplate at the top, then all the code we went through. Then we see the 2 subroutines we wrote in the last episode, print hex and print hex digit. We wrote them in a way that made them easily reusable, so they didn't require any modification to be used with the new print reg subroutine. We created another build script for the program, which we called stack.asm, which we built into a program called stack.prg. So let's go to the terminal and build it. So we are in the lesson 5 subdirectory, and we run build.sh, and then we can see that stack.prg was built. Let's fire up the emulator now to test it. Alright, let's maximize it. Now let's load stack.prg, and then we'll run it. That was pretty quick. We can see that table we were hoping for with that header in all caps at the top. What we didn't know going in was what those initial register values were going to be. So now we can see exactly how BASIC left those registers and how deep the stack is already in the first data row. The second row sees the hex 12, 34, and 56 values we expected in A, X, and Y respectively. The third row shows the result of the first push, which decrements the stack pointer as expected. The fourth row shows the result of the transfer of the stack pointer into X, so now they match, as you can see. We also see the status change to have the end bit set, which is due to the stack being less than half full and the high byte is now set in X, which could be interpreted as a negative value. In the fifth row, we see the result of pushing the status register to the stack, which decrements the stack pointer again. Then in the sixth row, we pull that status value into Y, and now we see those 2 pairs we were expecting, with X matching SP and Y matching SR. Finally, we see on the 7th and last row the result of pulling the old A value into the status. But something doesn't look right. A had been set to hex 12 before the push, as we can see in all the rows since then. But why doesn't the status match? Well, as you may remember from our discussion on the status register a couple lessons back, one of the bits, specifically bit 5, is not used. In fact, anytime you push the status byte, the 6502 will always set that bit in what gets stored on the stack. So whatever you have pulled it to won't stick around, as it's not really a register. There's nothing actually hanging on to that bit value. So that's why we see hex 32 instead of 12 printed out. That extra bit changes the upper nibble from a 1 to a 3. After the table is printed out, you can see that the stack was not corrupted, as evidenced by the basic ready prompt that comes back after our program finally returns. So that's it for this episode, our shortest yet. Not a huge amount of material to cover, but proper stack use is absolutely essential for a successful program on most computers. Unless you are on an Atari 2600, then there is no dedicated stack. If you want to see how scary that is, go back to my channel, please subscribe and click the bell to get notified when my next video comes out, and then check out some of my 2600 development videos. Thankfully, the X16 is a much easier platform to program for. If you are enjoying it, please like this video and let me know what you think in the comments. There's a lot more to cover in this series, so if these videos keep getting more feedback, the quality of future videos can keep improving and better help you in your learning experience. If you want to help even more, consider being a patron. People who pledge as little as $1 a month get early access to these videos and an inside look at how these videos are made and an opportunity for more direct and private communication. You will also join these fine folks at the end of all my videos, and higher pledges come with even bigger perks. So check out my Patreon page linked in the description, as well as the GitHub repo that has all of the materials for this tutorial series. Thanks, and I hope to see you next time. Bye-bye!